And if you want more details, you can go to the paper, which is in press now. Thanks.
Thank you very much, Paula. This is really exciting work. So let me ask the first maybe question. Obviously, please raise your hand if you have any questions, but let me get started. So do you actually try to throw out blazars from your sample? And or you actually I just wonder, how do you treat ordinary isotropic AGN versus blazars?
Yeah, so since we have these previous classifications from Milikvas and Roma, we knew which sources are supposed to be blazars, so we didn't include blazars for the visual inspection. So it was just a way to test whether our technique is selecting them as anomalies, because they are supposed to be anomalous for the quasar variability. So then we check only the sources without radio emission and sources which are classified as core-dominated or host-dominated. So from those is the original sample that we use to select the candidates.
Sounds great. Ilsa, you have a question?
Thanks, Paula. Just a quick question. Very nice work, first of all.
Thanks.
And I'm just curious, when you say the spectroscopically confirmed, that means that the spectral shape itself has changed?
Yes, I don't have the details, but I received some comments by Matthew saying that he already confirmed 2 of the candidates and 4 from his previous work, and there are 28 in common. So I don't have access to the data yet, but he is also observing the rest of the sample. So we hope that in a few months we will release the full set of confirmed candidates. But at least we know that there are at least 2 that are spectroscopically confirmed, but I don't have access to the data yet.
Yeah, thanks. Looking forward.
All right. At this point, we should probably move forward. So let's move on to Iva. Go ahead.
Thank you. Hi, everyone. Today, we report on CMP non-parametric modeling of AGN light curves within the framework of LSST Science Opportunity number 14 by Iva et al. 2019, as well as LSSTC Data Enabling Science. Building on previous tools based on Gaussian processes, autoencoder and then random walk for AGN light curve analysis and modeling, we have developed CMP as supervised training in an attempt to approximate function given a finite set of observations. While traditional methods don't handle irregular time sampling and require additional parameters, CMP can handle nonlinear data without adding extra features into it, as it is the case with more conventional statistical models. The animation represents the CMP process. Red dots are observations. A non-on function, which we are trying to find, is a blue line. X's are in our case time in modified Julian date, and Y's are measured flux in Miliansky. We want to find values of flux to obtain the realistic and uniform representation of the light curve. Our model consists of an encoder, aggregator, and decoder. The encoder generates individual representations of context points, which is meant to have all the information of the blue curve that we have obtained with these few observations. Aggregator combines them into one unique representation, and decoder takes representation with target points and outputs the mean and the variance of the probability distribution. Next slide, please.
Okay.
Thank you. In this research, we have processed 153 optical light curves from all sky automated survey for supernovae telescope. Each object has between 100 and 600 observations, which cover up to 5.5 years. This data sample makes a good representation of 80% of the sky with an irregular density of observations, gaps, flares, and possible QPOs. Plots for Farrell 9 and NGC 7469 show final results of modeling AGN light curves with different features after 300,000 iterations. We can see that CMP is quite good even when we have an irregular structure, changing gradient, big gaps, or random flares. For Farrell 9, we have representation which with and without measured errors, including in processing. The animation shows the training process for NGC 5548H beta light curve during 25,000 iterations. Dark blue dots are actual measured values of flux, while the green curve represents predicted values in target points. Execution time depends mostly on the number of observations due to vast amount of data expected in LSST. We have attempted to optimize our code by implementing parallelization Python modules. During testing on supercomputer, we have detected speed up of up to 63% while testing on 4 cores. The results suggest the CMP is an adequate method for modeling stochastic data with random gradient change, but at a cost of larger number of iterations and hence significant execution time. Therefore, some of our plans include further code optimization, implementation of mass processing, and comparison with Gaussian process in time efficiency and accuracy of modeling. Thank you.
All right, thank you. We have time for one quick question. So please go ahead, raise your hand. All right, I don't see anybody who's raising hands, so let me move on to Isidora.
Hello, everyone. I am Isidora, a PhD student from the University of Belgrade, and I'm going to report on the progress of the second subtask of our LSST Enabling Science project concerning the estimation of broadline region radius of AGN using a method called photometric reverberation mapping. The key is to find a time lag between continuum and line emission, which is a consequence of the broadline region light travel times using only photometric light curves. Usually, this is performed using resolved line spectroscopy, which is more accurate but observationally time-consuming. There is one difficulty with photometric light curves. As seen on the picture on the left, different LSST filters cover different groups of spectral features, so a broadband light curve is unable to trace emission line variability separately from the continuum. To account for this, Chalush and Daniel developed an efficient, although less sensitive method, which allows the utilization of these light curves for time lag estimation. Consequently, care must be taken when choosing filters, so they cover emission lines with significant contribution in the total integrated flux in order to successfully disentangle continuum and line emission. Having in mind the upcoming streams of light curve data from the LSST, this method could contribute in the dramatic increase in number of reverberation mapped objects, especially in the case of faint objects, which are difficult to monitor spectroscopically. Next slide, please.
Okay.
Thank you. The formula on the top left is the crux of this method. It represents the cross-correlation function between the continuum and the line, described as the difference between the cross-correlation and autocorrelation functions of light curves in specific filters, covering the continuum plus line emission and continuum emissions exclusively. Our goal is to use this method and develop a Jupyter notebook, which could be used to obtain time lags from LSST light curves. For this demo, we use observed photometric light curves of NGC 4395, which is a low-luminous Seyfert-1 galaxy, with expected time lag of the order of a few hours, as confirmed by the spectroscopic methods. We will focus only on the light curve segment from the first night, as seen on the middle panels. Additionally, we apply the neural network, described previously by Iva, to the observational data from the first night, as seen on the right panels. Using these light curves, we will estimate the AH alpha time lag. Next slide, please.
Okay.
Thanks. Here we can see the first results of our analysis after applying the method to both observational data on the left and learned light curve data on the right. On the bottom panels of both figures, we can see the CCF obtained using the mentioned formula, where the first peak indicates the time lag value. As you can see, the estimations are comparable in the two cases we explored and to the results obtained using spectroscopic reverberation mapping methods. As mentioned, the main goal of our work is to develop a Jupyter notebook for time lag estimation from LSST light curves. Some of our related future plans are listed in the orange box on the right, and every input and feedback is more than welcome. Thank you.
Okay, thank you very much, Isidora. So let me just put Viktor's slide first, but I certainly would like to open the floor for questions. Well, I have a question which is, just begs the answer here. Have you at all thought about possibly applying your technique to cross-correlation between optical and X-ray data? Because many of the sources that are actually in your sample are really well monitored. I'm pretty sure Alex Markowitz and maybe even before that, Rick Edelson worked on 7469, on Terrell 9, and so on and so forth. So what's your take on that?
We didn't think about that for now, but we are focusing only on the data that will be available from the LSST. So we are looking in this, just in this wavelength range from the LSST for now.
Yeah,
Thank you for your, yeah.
I personally think of this as being much broader and potentially scope than you even are showing here. So great,
Yes.
great. Anything else? Anybody else? Any other questions? If not, I believe this might be the last talk, which is by Viktor. So go ahead.
Hi everyone. Do you hear me?
Yes, we can hear you fine.
Thank you. Hello everyone, my name is Viktor Radovic, and I will report on the current development status of our Pythonic tools that our Serbian in-kind team created in response to the LSST's call for designing metrics for evaluating survey strategies in the context of AGN variability. The accent of this talk is on the developed software environment, for which the scientific justification is given in our paper by Kovacevic et al. In 2021. We developed tools that incorporate two metrics, one for unified time lags and periodicities, and the other one based on the structure function. For any input OPSIM cadence, our tool can simulate artificially generated AGN light curves, and those Python methods and classes are flexible, as user can change the parameters and the empirical relations used to generate those curves. We calculate time lags, periodicities, and statistical measures for each generated light curve using our classes. Then each heterogeneous mock LSST light curve is turned into vectors in the parameter space, which are then subjected to our metrics and our analysis is performed. These Python classes are submitted to the LSST MAF, and we are waiting for performance evaluation currently. And these classes are AGN structure function metrics and AGN periodicity time lag class. On this slide, we can see UML diagram for each class. And also I would like to mention that our code is publicly available on our GitHub repository, and the link is shown on this slide. Next slide, please.
Okay.
Here I will demonstrate briefly the usage of one of our classes. This is AGN structure function metrics class. First, of course, we create an instance of this class, and the only required constructor argument is absolute path to the selected OPSIM. We can choose any available OPSIM realization. It depends on the user. And also, beside that, we can choose the coordinates, we can choose the filter, we can change any other predefined parameter using setters, which are also available in the class, which we can see also on this example. And it is important to mention that all these parameters have default values, so it is not necessary for the user to choose. To run the whole code, we need to execute a run all function, and internally this function will calculate structure function for artificially generated AGN light curves. As a result of the execution, we can obtain raw data and different plots which are shown on the right side here on the slide. This plot shows heat maps of deviation of SFs. Also, they can show densities of summed metrics across different redshift or time scale of structure functions. And execution time for our tool is a little less than 40 seconds, but currently we plan also to reduce it more using parallelization. Every input and feedback is more than welcome. Thank you.
All right, thank you very much. Viktor, this is great. Looks like the team, and I believe all of you are in the University of Belgrade, right?
Yeah, we are all.
That sounds great. This is really wonderful set of presentations. So Thank you very much, everybody. We're almost exactly at the time, at 11 o'clock hour. So at this point, we are going to stop for just 1 second, allow for the participants who are just listening to the talks to leave. But presenters, please don't go away, because you're going to be presenting for the second time, starting in about, maybe 2 minutes or so.
Great.
Okay, so any participants that want to move to another room to listen to other talks, please feel free. And those of us who are presenting here or moderating here will just stay.
Greg, just to apologize, I have been stuck in the main room and I have been late, so I'm sorry for this.
Absolutely no problem, Andjelka. This is just fine. You know, everything is working very well. And looks like your team is really quite excellent, you know, in terms of presenting all this really wonderful time variability analysis tools, which is something that, of course, needless to say, it's very close to my heart.
Thank you so much for your kind words, and we will work on to improve this more. So if I can help you somehow more, because during this session.
Oh, it will be, no, don't worry about it. We can just, we'll just continue the way we did. Okay. The one thing that I would like to ask you to do is if you can connect and watch the, any questions in the Slack channel.
Okay, yes, I have opened Slack channel. And,
yeah,
and there was a question from Rahul Biswas. Is there a Slack channel for questions per breakout room? However, Ranpal answered that Zoom chat should be used. So we do not have some specific Slack channel for each room. So it can be posted here, questions, or either in the Slack. So I will monitor both of these channels.
That's wonderful. Thank you so much. This is important. Okay, so I'll give people maybe another minute or two, and once that starts, we're gonna start. Let me just move things back to the original set of slides. I think we probably don't have to repeat the general announcement slides. So
perhaps all people already heard in other rooms, and we can just skip it.
Just skip it. That's right. Yeah, so those two slides are basically reminders about the fact that you abide by code of conduct. That's the first one. And second of all is that we're recording this, and the videos will be posted the next day. Okay, it is 2 minutes past the beginning of the hour, so maybe we can get started. And again, we'll start with Faye again. So I hope you don't mind repeating the same talk as you did before. Thanks, Faye. Go ahead.
Sure. Hi, my name is Faye Davis, and I'm a first-year PhD student at the University of Hertfordshire. My current research has focused on radio AGN in dwarf galaxies, and since dwarf galaxies dominate the galaxy number density at all epochs and all environments, it's important to understand their evolution. And since AGN are thought to play a key role in evolution of massive galaxies, it's important to understand if they also influence dwarf galaxy evolution. So in our study that we have done, we have identified 78 dwarf galaxies that host a radio AGN using a combination of optical HSE data and the low-fi radio data in the Elias N1 field out to a redshift of 0.5. Could you change the slide, please?
Sure.
So we looked at the optical data in order to underpin the primary triggering mechanisms of the AGN in these systems by comparing them to a control sample matched to their redshift and stellar masses. So we studied their environments by comparing the projected densities to their nearest neighbor massive galaxies. And as shown in the graph, we found that the nth nearest massive galaxy to the AGN were always consistent within the error bars to the controls. And this was also the case for the tidal fractions, where tidal features were identified in the AGN and the controls via visual inspection. So this ruled out triggering via mergers. And lastly, the consistency in the star formation rate and the colors of the two samples suggested that the gas masses that are driving the star formation are similar in the AGN and the controls. So this means that the AGN are therefore not gas enriched compared to their control counterparts. Can you change the slide, please?
Sure.
Thank you. We underwent radio analysis by employing a semi-analytical model of radio galaxy evolution to extract accretion rate estimates for a suite of about 100 low-fi detectable Monte Carlo simulated AGN. And given the lifetime of these AGN, we calculated the total gas mass accreted, and the central gas mass within these dwarf systems as predicted by a hydrodynamical simulation, is over a magnitude greater than that required to maintain the AGN. And this essentially means that there exists an ample supply of gas within dwarf galaxies, within its intrinsic gas reservoir, to drive the AGN. And furthermore, since our analysis has shown that special circumstances are not necessary to trigger the AGN in dwarf galaxies, it suggests that AGN triggering in this regime is likely to be stochastic in nature. So can we go to the next slide, please?
Sure.
Thank you. Lastly, the mechanical energy output of the low-far detectable AGN are shown here to be nearly 2 orders of magnitude larger than the predicted binding energy of the dwarf galaxy systems. And this indicates that negative AGN feedback is plausible in these systems. So in the paper that we've just finished writing, we have shown that there exists accreting black holes in dwarf galaxies in the nearby universe. And we've also found that they are likely to be a common phenomenon. And I'll finish this quick talk by stating that important studies like this can be a roadmap for LSST combined with SKA in the future. Thank you very much, and that's the end of my talk.
Thank you very much, Faye. This is great.
Cheers.
We have time for questions. Dragana, go ahead.
Hello.
Thank you, Faye, for very interesting talk. I'm really impressed with the results shown here. I'm going to definitely check the paper. And I was just wondering, have you been estimating the range of masses of the supermassive black hole that you have in your sample?
No, well, we haven't been able to do that because the sources aren't extended, so we're not able to resolve them. The radio analysis side of things that we've done is we've used a model to kind of with a similar range of radioluminosities as the AGN that we have found. So we managed to like infer certain properties, but not like the exact properties, if that makes sense.
Well, anyway, it would be interesting maybe to see, I don't know, whether you have like optical spectra from these galaxies and like whether they show emission lines and whether you can estimate something from this. Anyway, I'm going to read the paper because I'm really also interested in environment of these galaxies, but I'm not going to waste the time here. Thank you once again for showing this.
All right, thank you very much, Faye, again. And this is again opportunity for you to contact the speakers directly. Sorry. All right, Paula, I believe this is your first one, right? First slide.
Yes, thanks.
Okay.
So hello, everyone. I'm Paula Sanchez Saez, and today I will show you the results that we recently published. This work is in press, but it's also posted in the archive. So the goal of this project is to search for changing state AGNs, also known as changing look AGNs, which are sources that change their classification between type 1 to type 2 or vice versa because of the transitions of the emission lines. So in this particular work, we use anomaly detection together with deep learning to search for these kind of sources. And this work it was inspired by the results presented by Superlab 2020, who proposed that these kind of sources can be classified as outliers when we observe their variability features like the damp random walk modeling features. And so in this project, we use a sample of more than 200,000 AGNs selected from the Miliquas and Roma catalogs with optical light curves in CTF data radius 5. We use T-band light curves for point sources, and we require a minimum of 2 years of data. And this method is now applied to CTF data, but in the future, the idea is to apply this to the Rubin LSST survey. Next, please.
Okay.
So we use a variational recurrent autoencoder, what was inspired by the architecture presented in Tachibana 2020, who used a recurrent autoencoder, but in this case, we slightly modified the architecture, including a variational side, and you can see in the left panel the architecture we used, and in the mid panel you can see the reconstruction error that we obtained for the sample. We used the reconstruction error as an anomaly score, selecting as anomalous all the sources with a reconstruction error larger than 3. And we also, for the sources with a proper modeling, we used the latent space attributes as a vector of features together with an isolation forest to search for anomalies. So in this case, we use a threshold of 2%. Next, please.
Okay.
So using this, we selected a total sample of around 9,000 AGNs as anomalies, and Here in the left panel, you can see the classifications of the different AGNs. So we have BLX, flat spectrum radio quasars, core-dominated AGNs, host-dominated AGNs. And we notice that most of the BLX are considered anomalous by the algorithm. And this is expected because we're training the model using mostly quasars, and BLX have considerable different variability. So we use blazars as a testing of the model. And we also notice that a high fraction of the candidates are sources dominated by photometric issues like underestimated errors, overestimated errors, or problems in the images like the ones that you can see in the top middle panel, where you have some problems in the CTF images, and also some sources were misclassified sources that are classified as quasars in the original catalogs, but then you can, when you see the likers, they look like variable stars. So we use this sample to select for the promising candidates. We selected 75 changing state AGN candidates. These were selected by searching for flaring activity or an abrupt increment or decrement in the luminosity. And we know that 4 of these sources are already confirmed by the work of Matthew Graham in 2020, and also 2 of them were confirmed spectroscopically by Matthew Graham. And also 28 are common candidates using other techniques that is a work in preparation by Graham. And now we're in the process of confirming spectroscopically the full sum. So stay tuned, we will soon release the full confirmation. And if you want more details, you can go to the paper, which is in the archive. Thanks.
Thank you very much, Paula. This is great. So if anybody has any questions, please go ahead and raise your hand. All right, I don't see any raised hands, so let me just move on to the next step. Next presenter is Iva, so go ahead, Iva, go ahead.
Thank you. Hi, everyone. Here we report on CMP non-parametric modeling of AGN light curves within the framework of LSST Science Opportunity number 14 by Iva Cvorovic, 2019, as well as LSST C Data Enabling Science. Building on previous tools based on Gaussian processes, autoencoder and damped random walk for AGN light curve analysis and modeling, we have developed CMP as supervised training in an attempt to approximate function given a finite set of observations. While traditional methods don't handle irregular sampling and require additional parameters, CMP can handle nonlinear data without adding extra features into it, as it is the case with more conventional statistical models. The animation represents the CMP process. Red dots are observations. An unknown function which we are trying to find is the blue line. X's are, in our case, time in modified Julian date, and Y's are measured flux in Miliansky. We want to find values of flux to obtain the realistic and uniform representations of the light curves. Our model consists of an encoder, aggregator, and decoder. The encoder generates individual representations of context points, which is meant to have all the information of the blue curve that we have obtained with these few observations. Aggregator combines them into one unique representation. The decoder takes representation with target points and outputs the mean and the variance of the probability distribution. Next slide, please.
Okay.
Thank you. In this research, we have processed 153 optical light curves from all-sky automated survey for supernovae telescope. Each object has between 100 and 600 observations, which cover up to 5.5 years. This data sample makes a good representation of 80% of the sky with an irregular density of observations, gaps, flares, and possible QPOs. Plots for Farrell 9 and NGC 7469 show final results of modeling gauge light curves with different features after 300,000 iterations. We can see that CMP is quite good even when we have an irregular structure, changing gradient, big gaps, or random flares. For Farrell 9, we have representation with and without measurement errors included in the processing. The animation shows the training process for NGC 5548 H beta light curve during 25,000 iterations. In previous actually slide, this is Isidora's slide.
I'm sorry.
No, it's okay. One.
Am I too far forward? Or?
Yes, previous and one more. Yeah, thank you.
Sorry.
The animation shows the training process for NGC 5548 age beta light curve during 25,000 iterations. Dark blue dots are actual measured the flux, while the light green curve represents predicted values in target points. Execution time depends mostly on the number of observations. Due to vast amount of data expected in LSST, we have attempted to optimize our code by implementing parallelization Python modules. During testing on supercomputer, we have detected speedup of up to 63% while testing on 4 cores. The results suggest that CNP is an adequate method for modeling stochastic data with random gradient change, but at the cost of larger number of iterations and hence significant execution time. Therefore, some of our future plans include further code optimization, implementing of mass processing, and comparison with Gaussian process in time efficiency and accuracy of modeling. Thank you.
Thank you very much, Iva. Again, there is some time for questions. We're doing quite well with time, so no need to be shy. I don't see any raised hands. In that case, let's move on to the next set of slides. So that's Isidora. Sorry about the advancing it earlier. So go ahead, Isidora.
Thank you. Hello, everyone. I'm Isidora, a PhD student from the University of Belgrade, and I'm going to report on the progress on the second subtask of our LSST Enabling Science project concerning the estimation of broadline region radius of AGN using a method called photometric reverberation mapping. The key to the method is to find the time lag between continuum and line emission, which is a consequence of broadline region light travel times, and using only photometric light curves. Usually, this is performed using resolved line spectroscopy, which is more accurate but observationally time-consuming. There is one difficulty with photometric light curves. As seen on the picture on the left, different LSST filters cover different groups of spectral features, so a broadband light curve is unable to trace emission line variability separately from the continuum. To account for this, Chellush and Daniel developed an efficient, although less sensitive method, which allows the utilization of these light curves for time lag estimation. Consequently, care must be taken when choosing filters so they cover emission lines with significant contribution in the total integrated flux in order to successfully disentangle continuum and line emission. Having in mind the upcoming streams of light curve data from the LSST, this method could contribute in the dramatic increase in number of reverberation mapped objects, especially in the case of faint objects, which are difficult to monitor spectroscopically. Next slide, please.
Okay.
Thank you. The formula on the top left is the crux of this method. It represents the cross-correlation function between the continuum and the line, described as the difference between the cross-correlation and autocorrelation functions of light curves in specific filters covering the continuum plus line emission and continuum emission exclusively. Our goal is to use this method and develop a Jupyter notebook which could be used to obtain time lags from LSST light curves. For this demo, we use observed photometric light curves of NGC 4395, which is a low luminous Seifert 1 galaxy, with expected time lag of the order of a few hours, as confirmed by the spectroscopic methods. We will focus only on the light curve segment from the first night, as seen on the middle panels. Additionally, we applied a neural network described previously by Iva to the observational data from the first night, as seen on the right panels. Using these light curves, we will estimate the H-alpha time lag. Next slide, please.
Okay.
Here, we can see the first results of our analysis after applying the method to both observational data and learned light curve data. On the bottom panels of both figures, we can see the cross-correlation function obtained using the mentioned formula, where the first peak indicates the time lag value. As you can see, the estimations are comparable in the two cases we explored and to the results obtained using spectroscopic methods. As mentioned, the main goal is to develop a Jupyter notebook for time lag estimation from LSST light curves, and some of our related future plans are listed in this orange box on the right, and every input and feedback is welcome. Thank you.
Okay, thank you very much, Isidora. This is nice. We had some nice questions in the previous session. So anybody from this session is interested in asking questions, go ahead. No, I don't see any raised hands. So let me move on to the talk by Viktor.
Hi everyone, thank you. My name is Viktor and I will report on the current development status of the Pythonic tools that are developed by our Serbian in-kind team. These tools are developed in response to the LSST call for designing metrics for evaluating survey strategies in the context of AGN variability. The accent of this talk is on the developed software environment for which the scientific justification is given in the paper Kovacevic et al. 2021. We developed tools that incorporate two metrics, so one for unified time lags and periodicities, and the other one based on the structure function. For any input OPSIM cadence, our tools can simulate artificially generated AGN light curves. Our methods and class and the empirical relations used to generate these artificial curves. For each of these generated light curves, we calculate time lags, periodicities, and statistical measures. And then each heterogeneous mock LSST light curve is turned into vectors in the parameter space, which are then subjected to our metrics. Our Python classes are submitted to LSST MAF, and we are currently waiting for performance evaluation. These classes are AGN structure function metric class and AGN periodicity time lag class. On this slide, we can also see a UML diagram for each class, and also the link for our GitHub repository where you can publicly find these classes. Next slide, please.
Okay.
Thank you. Here I will demonstrate briefly the usage of one of these classes. This is AGN structure function metric class. Of course, first we create a class instance, and the only required argument is an absolute path to the selected OPSIM realization. Any available OPSIM can be chosen. And also, beside that, it is possible to set a different set of parameters, such as equatorial coordinates, filter. Also, we can change the settings for noise, amplitude, etc. And for that, we can use a setter function which exists in this class. This is also shown here on the example. Also, it is essential to mention that all these parameters have some default predefined values if some user don't want to change them. In order to run this class, we need to execute the run all function. Internally, this function will call the SF function, which calculates structure function for our artificially generated AGN light curves. As a result of the execution, user can obtain raw data. User can obtain also different plots, which are shown on the right side of the slide. These plots are heat maps of deviation of SFs for selected OPSIM cadence, and also densities of summed SF metrics across different redshifts, for example. And the execution time for our code is a little less than 40 seconds, but we plan to reduce it by using parallelization in Python. Every input also is, of course, more than welcome. Thank you.
Thank you very much, Viktor. This is really wonderful. Again, it's nice for me personally to see it for the second time, because I pick up more and more from every time I see the presentation, so it's great. All right, there's plenty of time for questions. I don't see any raised hands, and let me just check if there's anything on chat, but I didn't think so.
No.
So no. Does anybody have a question?
No questions in Slack, neither in chat. And maybe okay. If presenters would like to add something to their talks, because they were only 3 minutes long, maybe something which was not pointed.
That sounds like a good plan. So even presenters, please go ahead, raise your hand, and I'll call on you.
Yes.
All right, I don't see anything. So maybe at this point, I will stop sharing. And what we can do is we can go back to the main room. And if any of you want to catch a tail end of another session, this is always, of course, perfectly okay. So thank you, everybody. And I'm gonna just close the room. And at this point, we'll move on to the main room. Thank you.